so I will speak about the Landau Gilbert equation, but with a slightly different energy. And it's a joint work, collaboration that started with Radu, and that I pursued with Guillaume Ferrière, who is a postdoc in Strasbourg. Okay, so this is the outline of the talk. I will first detail my magnetic energy, which has some things that look like what Matthias told us, and also some relation to the previous talk by Susanna. I will speak about again, but briefly on the equation, and speak not about self-similar solution, but domain walls, which are rather natural in this study, and I will give the results. Okay. Okay, so the energy that I will look at is essentially the complement of Matthias' energy. So in the micromagnetic energy, you can look at many different terms, but the one you really want to look at, you can't forget, is the exchange energy. That's what it's about. Then there is the straight field or magnetizing field, which is the non-local. Here, so it's something in the whole space. And in this talk, I will also consider two types of energy. I will assume that there is an easy axis anisotropy, that magnetization will align with the E1 line. So the first component of the magnetization will tend to be -1 or +1. And also, in fact, for our analysis, it will be deal with the DMI, the Lifschitz-Gilbert interaction, which accounts for an anisotropic exchange energy. Here, so yeah, and I have some parameters: D for the exchange length, Q for the quality factor, and D for okay, and when you see this, then there is a natural energy space, which is the H1 dot norm, and well, M has to is its value in the sphere, so actually 1 minus M1 squared is simply M2 squared is MC squared. As Matthias mentioned, there is no further square, and so this is the norm of the last two components of the magnetization. Okay, and I won't deal with a 3D model, actually. I will deal with a 1D model. So I want to look at nanowires. This is where I can perform the analysis. So I have 2 slides to tell you a bit how I will go from the 3D model to the 1D model. So I look at a cylinder, length L and diameter and section, a disk radius R, and I do a scaling. So I scale in the E1 direction, and in the scaling by R. So the energy that I mentioned before, we scaled from the energy. And if I want to do this properly, then, but in the end, I want the length L or rho to length from infinity to get the whole line. And so the functional space that I look at is essentially when I'm is I extend M by a constant outside the cylinder. And okay, so I will choose a regime where everything works. So it's where I can do the analysis, and it corresponds to a high quality factor exchange length, very thin and rather short. It's not very long, so it would be a line in the end, but it's a few nanometers, right? It's not too long, but in the end, I still get a nanowire. So this is physically somehow relevant. What is a bit less relevant, and way of this thing is that we have to neglect the straight field, otherwise it gets in this. But the straight field is exactly what Matthias worked a lot on. And but when you add a straight field, then you have nail wall, and that's a different business. Okay. Okay, so you rescale according to the this term. So this term is, you want to take the limit, you have 1 over eta, so it will impose that in the limits this gradient, which is the gradient of the last 2 components of the magnetization. This has to be 0. So you have something which is a constant in the E2, E3 direction. You get these 2 are will remain at the limit. Then you have the Olszynski-Moria interaction, and you will make assumption on the D prime factor, essentially, so that this guy tends to 0, well, needs to be 0, and you will make an assumption so that this converges, and you could say it should converge to any real number, and actually we will assume that it converges to some gamma which is between -1 and 1. I don't know if there is a meaningful signification to the fact that we need to be in the open interval or not, but again, for the next analysis to work, we really need to have this gamma in this bounds. Okay, and similarly, I will mention that I wanted to get rid of the straight field, so I do some assumption on the regime, and what I get is the gamma convergence of these eta to 0. This is the real energy that I do at. So it's gamma convergence in the weak curly H1 topology. I won't say more about the gamma convergence. I think it's very standard for you expert. For you, it was new. But okay, so the main point is to get a coercivity property to actually to absorb the TMI interaction. This is the one term that well, you can do it provided that gamma is in -1. Okay, so this was for the micromagnetic energy, and now I want to talk about the evolution of the magnetization. So as Susanna told you, a very nice model for the evolution is given by the Landau Lifschitz Gilbert equation. So here the beta is 1, I rescale so that the beta is 1, and I have my damping factor, and the difference is that the total magnetic field H of M is a bit different now from Susanna. I have extra terms. So it's actually the sum of 2 terms, H. This should be E1. So there is the intrinsic energy, right? Which looks like which is the limit energy that we got. So now we are 1D models. So this is norm, then the DME my term, and then the anisotropy easy access.
Has the sign changed on the gamma term? It was like it was negative.
Yeah, well, gamma is -1 and 1, and actually everything everywhere it will be 1 gamma squared theory. So yeah, maybe no, I think it's correct because this is the way I wrote it. If I wanted to have the E1 outside, then you have the triple product as a determinant, so you get a minus. Okay. Probably it's correct. I think I copy paste from the paper, and you know, Radu is very thorough, and so I'm pretty sure that's okay. And this is the term, so it's written correctly here. You have an external magnetic field, and I think for the physics it's very relevant because also all the nanowire models, physicists are very happy about it, or our industry is very happy about it because they're meant to be like the next generation for storage, data storage. And the idea is that you apply a magnetic field, and at least if you have one particle, one microparticle, then spin up is 1, and spin down is -1. And you want to apply a field, an external magnetic field, to change this value, and you want, for an you want to do it fast and cheap. So the external field is it's quite important. And yeah, and the magnetic field, the point is that it's not in, it's homogeneous in space. So this is what I can do, and it favors E1. So E1 is favored by many things in this business. Nevertheless, the equation has a few group of symmetries. So you have space transition along the nano wire, and on the control, you have return for rotation. So this is you have an action. I write G dot M, the action of this symmetries for magnetization. And what are domain rules? Domain rules are transitions. So in my functional setting, I'm in H1 dots. So I have limits at plus and minus infinity, right? And this the values or the limits are E1 plus E1 or minus E1, right? So the domain rule is a transition from say minus E1 to plus E1 or the other. It's a fixed transition. And it's a phase transition that is a critical point for the energy. So as you have the constraint that the magnetization has norm 1, you get a Lagrange multiplier, which means that the derivative of the energy has to be aligned with M. And another way to put it, you have this equation. So our first result with Radu is that there exist domain walls, and you have only one of them up to obvious, easy symmetries. This form, and it tells you that you have one function, which is a theta star. So maybe I write the first component that is interesting. This. And yeah, this is simply in a spherical coordinates that I have theta h1 and gamma x in the spherical coordinates. So this function is where the information lies in this thing. And the point is that in my setting, then because I have an applied field, an external magnetic field, it's not a solution of the LLG equation, but I have to add a precession, so it moves. And the precession is also extended. So translation in according to the applied field. So the applied field controls the way the domain walls moves, and also it also controls the speed of the precession. So how do we prove that there are no other domain walls than this equation? So this equation, this formula was found by physicists, I guess, in the early 2010. And how you prove that you don't have any other? So the idea is first to heal the phase by you take it away. It doesn't depend on H. It doesn't depend on H. So you take it away. And then you prove that the solution will be planar. So up to an extra rotation, you can assume that it lies in the E2, E3 plane, and then as it has modulus 1, then you can parameterize by an angle theta, and then you're in business. Okay. So now I want to study the stability of these domain walls. So I have first to understand the flow. I have to prove that there is a flow. So this is local one-opposedness, and maybe you're a local, I hope you're a local expert on local one-opposedness. So I want to discuss a little bit on local one-opposedness for LLG. And Susanna could tell you that also that local one-opposedness is very tricky. So for Schrödinger maps, it's well known in the dispersive equation really very hard, and you don't have a very satisfactory local work-closeness, and you have very deep results, especially when you were from say RD to SD. Assuming that you have a solution, you have like persistence of regularity, and these are deep results by Begenaro, Ionescu, Koenig, and Tataro, like the Romanian team. Koenig was. Well, they have a few papers at Anazov Math on this, but they have to assume that there is a solution. So it's they assume that they got a smooth solution, which is small in some HS, critical HS norm, and then they prove that there is persistence of this smallness. It's very deep, but it's not the flow. So it's even their deep result is far from what we would like to have, which is given an initial data, then you have, at least for small time, say, a solution which lies in the same space. Well, in 1D, it's much better because you want to work in H1. Well, you're allowed, it's meaningful to work in H1, so you are what we call subcritical problem, and H1 is embeds in continuous functions, so it's very favorable. So there is this local well-posed theorem, and we would like to have it at least dimension 2 or 3, maybe with a index k. Could be 1 or 2, maybe. So the function. So anyway, you have to take care about the functional space. And what we took is when we want to go to higher index, is that you have the full L2 norm for the k derivatives, and you have the L2 norm of the last 2 components of the and this theorem tells you that if you give yourself an external field and a magnetization in this space, for k at least 1, then you can construct a unique, strong, well, mild solution, which is continuous with values in curly H. And well, you cannot a priori rule blow up, that is concentration of energy in one, you cannot rule it because you have the external field. That field, so it's a Dent equation. So there is some decay here, but you feed also energy with the external field. So if you have a large external field, you do have, at least numerically, you do have blow. But if you have blow up, then the curly H1 norm has to blow up. And also, this is the important thing to work with business. If you have continuity of the flow, if you have one solution, then in the neighborhood of this solution, all the solution do not blow up too early and have continuity of slightly below, slightly before the blow up time. And if you're smooth enough to make sense of the terms, then you have a dissipation equality. That is, the derivative of the energy has a meaning. So you have this term. I wrote it like this. So it's the essentially the component of dm, which is orthogonal to n, which means the space in the sphere. So the good thing is that this is positive, and you have a term which is related to the external a bit complicated. And also what you can see is that, okay, n is at norm 1, so this is a term of quadratic term. But here you see it's a linear term. So if you do variations and you're not lucky, then yeah, this could be much bigger than this one here. Okay, so on the functional space, we choose like this, but in fact, well, you have to work a bit, but you can see that you control all the derivative between 1 and k. So in fact, you control everything except for the m1. Without derivative, but you control m1, the derivative of n1 as well, with the curly h. The other point is that if you are looking around one specific magnetization, if you're looking around one specific magnetization which satisfies some non-degeneracy condition, And the domain wall does satisfy the condition. If you look at a small neighborhood in curly H1, then it's exactly an H1 neighborhood. So yeah, curly H1 is more natural with respect to the big flow, but when I'm looking at what happens around domain walls, then actually curly H1 and H1 are essentially the same. Okay. So for the so I have this half slides on the local well closeness. So the point is that if you look at it as a Schrödinger map equation, then it's quasi-linear. So it's pretty nasty, and usually you need when you have a quasi-linear Schrödinger equation, you need to do you have the word by tells you that what you can expect about local well closeness is HS for very large S, not S is 1, 2, T over 2. However, well, there is a way to use the geometry of the equation and makes it much better. And there is also a way to use the dissipation, which gives you parabolic effects. So the idea is to do a stereographic projections around a point that M0 does not touch. And such ones do exist because you're on the line, and you have limits at infinity. So it's not dense. The image of M0 is not your stereographic projection, and maybe it answers the questions about how is this dissipative. It's dissipative in the alpha here. So the one corresponds to the Schrödinger equation, and the I alpha gives you the heat equation. So here. And then you have these terms. So these terms is a bit like harmonic map equation. There's lower order terms, but well, because it's the heat equation, it's still manageable, and you're in dimension 1. It's still manageable. So yeah. So this is how you prove this local representation.
Which space do you use to solve that?
So we didn't wrote it. Really, it's so it's Cato first did this, but you can do it in H1.
Yeah, which energy is dissipative?
Sorry?
Like all these HK norms are.
No, I think well, you could write an equation for the higher order things, but well, you will have inequality, but not as nice. Yeah, it can certainly be useful if you want to speak about, for example, asymptotic stability in higher order solid space medium.
Why H1 over 2? You're not on the real line?
Yeah, it's or H1 of R, R2.
Yes.
Sorry, thank you. Okay, so now I can say do the result. So how does it go? Okay, so you give yourself. It's really, I think, really the results you can ask about asymptotic stability. You give yourself a magnetization in curly H1, which is close. Okay, so it's stable. The sigma should be upstairs, and the sigma corresponds to here the plus and minus. So it's sigma. So it should be an exponent. You're close to one domain, only H1, so in H1. You've done closed, and you assume that your external field is small. Okay. Then the solution is global. You don't have to go up. And actually, it converges the magnetization up to a gauge. Converges exponentially fast to the domain wall. And the gauge, G, is limited. And up to a fixed gauge, it converges also exponentially to the gauge given by the precession of the pure domain. So there are other stability or asymptotic stability for walls, but in a slightly different setting. And probably the first one is by Carbou and Labé, and then you have the few other by the students, Radu, and also another one by Takasao. But it's for different domains, which are not precessing. And what is important here is that I think maybe all results except one have no external field, and when they have an external field, it's a constant field. And when it's a constant field, then it's very different because they can perform the analysis that I talked about, and also they don't have the Lifschitz-Gilbert interaction. To do the proof, there was a physics paper by Wu, Bousset, Robbins, and Slastikov, where they do linear analysis. Linear stability without the EMI interaction. Well, I think that probably their analysis could encompass the EMI. I'm not. Anyway, we did it non-linearly, so it's separate. So the point is that when you have a constant external field, then the domain world is really it's like a fixed object, and then you can do a linear analysis around this fixed object, and using you have enough argument, and you can really study the linearist flow. The point is that you can it's the linearist flow that you can see. They put in evidence a spectral gap, which is in the bottom. It's always what you need, and very important. The point is that when you have a varying field, this collapses. I don't know how to do it. And as I mentioned, it's important for me for these problems. And also, I have also some ideas to do some control theory on this and to use the magnetic field as a control. And the idea is to extend, not work on the flow. I don't want to look at the linearist flow. I want to look at the energy and for this I will use modulation theory. So this fits somehow in the general idea of Weinstein for dispersive equation and to study the orbital stability of solitons. And I think Philippe mentioned it a bit, and also Elliot in the same kind of ideas. Of course, it's a bit different because here, well, the technicality are because we have this non-convex constraints that the magnetization has to be to the sphere, and the technicality changes a bit for the modulation, and I will speak of it later. So apart from modulation, the one idea that we required is to write the equation in the appropriate form. And well, we had to come up with this frame and do some computation in this frame. So W star, N star, which is explicitly like this, the derivative in the theta direction when you write it in a spherical coordinates, and P, which is the derivative in the phi direction. We normalized. So you assume that you have a small eta, so that you assume that your magnetization rate are the sum of the domain wall plus this eta on this so it depends on x. And what you see, and this is not too surprising, is that but it's crucial actually. The W star component mu is quadratic. So because you have to be on the sphere, so you have to remain on the tangent plane somehow. And so this is true pointwise. It is a pointwise equality. And when you integrate it or take derivative on it, then you can see that actually the HK norm of eta is essentially the norm, some of the norm of the last two components. The new components completely disappear. Okay. In the next slide, I will detail some other bounds, and I'd like to introduce this notation, big O, and I have two indexes controlling the usual notation. One index is for the degree, so k equals 2 is quadratic, is cubic, etc. And the L is the number of derivatives that I'm allowed. That I have to. So I will obtain a pointwise bound, pointwise expansions, and then I want to integrate it. And I have to count the number of derivatives. The integration I want to have solvable. Global bounds after integration in space. For example, mu is simply quadratic in eta with zero derivative. Okay, so when I expand the energy, then I have this thing. So you have to imagine that n is W star plus theta, and theta is small. So I recall that the energy is like this. So I compute this term pointwise. So the leading term is this thing, and then somehow W star has it's a minimizer, so you don't have linear terms. And you look at the quadratic form, and it writes very beautifully in the frame that I chose. And you have this operator, this Schrodinger operator, which is written here. It's always the same. So for each component mu and rho, it's the same, and you have no other components in mu because it's quadratic. And the errors you make are cubic, and they have at most two derivatives because you have two derivatives. Okay, and then I compute the dissipation. So, and again, I think I found something which is beautiful. And again, I have this operator L, and now it's the square of LU and square of rho. And the error terms are cubic. And now I have four derivatives because this is quadratic. And if I look at the forcing term, well, you can do the expansion. It's difficult, and I have no rho contribution. So it's linear, as I mentioned, it's linear in eta, but only on the new component, given by a fixed function depending on theta. And again, I have two derivatives, so the error is quadratic. Okay.
Sorry, I'm confused. The lower index is not the maximal order of the.
No, the upper index is the lower index is the maximal number of derivatives, is the number of derivatives.
You don't have a fourth order derivative in your expression.
No, it's the total number of derivatives. Yeah. Yeah. So you don't have four, but yeah, you have two. Okay, and so obviously we have to study the this linear operator L, and well, it's 1D, so we have trivial means pretty easily. Actually, I think it's a well-known operator in short theory. It has one element in the kernel which is explicit and which is positive. So Sturm Liouville tells me that you have a gap, and actually the absolutely continuous spectrum is start as 1 minus gamma squared. So up to this thing, this vector, it's definitely positive. So yeah, so this is it's one. So you have a zero and zero first. Okay, so then you can integrate in space. And this my big O, pointwise big O notation that I use is amenable to Sobolev bounds. So for the energy, it's everything is fine. And this will have almost coercivity. And for the derivative for the dissipation quality, then you have these terms which are very nice. Then you have I cheated a bit. This should be the next slide. So in the end, I will have this. Right now, I don't have this. I have this linear term first. I have this linear term with a. And let me just mention that you have to be careful here. It's not cubic in H2. It's slightly better. It's quadratic in H2, and you have an extra term in H1. So yeah, I have an H term here. It's not yet quadratic. Will be correct. If you know that you're orthogonal, if you know that the eta is orthogonal to 5 somehow, then it will be correct.
So the Maya signs are without square.
Yeah, it should be squared. Okay, so now we'll speak a bit about modulation, and the modulation is essentially to. Okay, so what is modulation? The idea is, okay, I have a group of symmetry of my equation, and I will transfer, instead of looking at the scalar product and looking at the flow of the scalar product, sin theta star comma eta, which could be done, but I want to look at geometrical, I want to look at the evolution of geometrical parameters. So what does it tell me? It tells me that if I give myself a magnetization, which remains close to a domain wall or some dimensional, then I can decompose it dynamically as a gauge applied to W star plus a small error depending on the time, and the error is of the order of the error that I make here. And what I gain by allowing this gauge is their orthogonality condition. And as my gauge has essentially two free parameters, then I'm allowed to have two orthogonality conditions. So yeah, you cannot choose them arbitrarily, but you have some. You have to be transverse to something essentially. But you can allow these two, and I choose these two orthogonality conditions. So there are two steps to prove this kind of modulation. One step is you do it for fixed time. It's a static argument, or you do it for fixed time around W star. And this is how do you do it? You do an implicit function theorem in the neighborhood of W star on this functional. So for a small gauge, W near W star, you look at what should be your epsilon. You do the scalar, you do this thing. You know that when J is 0 and W is W star, this is 0, and you do an implicit function theorem, R2 essentially. So it's finite dimensional. And it gives you for free that G depends exclusively on W. Okay, so this gives you for fixed time this thing and this thing. And then you want the dynamical equation. So what you do is you plug in the equation this, and you do the scalar product with this guy and with this guy. And well, the derivative of the scalar product will make you appear the components of G. And the terms, there will be at least linear in epsilon. And essentially, you cannot do parallel. It's really when you perform the static arguments, you can do it at the level H1. But when you do it, when you want to do it dynamically, then you have to be careful. And this is the difference when you do modulation for the Schrödinger equation, for example, where you can remain at H1 and you say, okay, I do it for a smooth function, then there is no problem, and then I do limiting argument. If you try and do the same thing for LLG, then well, things behave a bit worse, and actually you need to work in an H2 context. This is not too bad because in the end we will use a limiting argument, but you cannot use the limiting argument to at this step. Okay, so then how does it work? I have everything. So once I do this modulation, what I gain from this condition is that this term H. Okay. So the idea to perform stability is to do a bootstrap argument. So the bootstrap argument is essentially a connectedness argument. You work on the maximal time interval on which you have a good bounce, and you improve the bounce. So as the condition is closed, the set of time on which it will work is closed, but as you improve the bounce, by continuity of it will be open. So close, open, and void will tell you that it's not. So how does it work? So you look at the maximal time interval on which you are near a domain wall. As you start delta, so you give yourself a large parameter of big A to be fixed in the end. And all the implicit constants do not depend on A. There are large constants, but independent of A. So at initial time, you're delta close in the curly H1 norm. So your C delta close in the H1 norm, non-curly H1 norm. So it's independent of A. And so you can start. T star is non-zero. So then you decompose on this time interval on 0 T star, you decompose your magnetization. And what you get from these things, and the fact that the mu component is negligible, is that the difference of the energy actually controls the H1 norm of epsilon. And what you get from the dissipation equality is that the energy of M decrease, like minus epsilon in H2 norm. And then you have your error term, and your error term is H, which is assumed to be small, and epsilon of T in H1, not in H2, but in H1. And as it is in H1, then it's small on this interval. So these guys are small. So it will tell you that actually the energy is non-increasing, and as it controls the epsilon, then epsilon will be controlled and not dependent. So you get a constant C times delta, and if you so you have a universal constant independent of A here, and you simply choose A is to C. So on this interval, you were able to improve on this thing, and then my connectedness argument tells you that T star is plus infinity and that epsilon remains small. And then you run once again the argument here essentially, and you get exponential convergence. So this is the H2 case, and for the H1 case, then now you use that the flow is well behaved in H1. Okay, so one point of doing this like this is all these arguments are amenable to localization in space, because not spectral theory, so you can do trade-offs. And one application to this is the stability, asymptotic stability of two domain walls. So you take two domain walls, so the one well separated. If I draw the M1 thing, it's this kind of configuration. And the idea is that you will have one domain wall going that way and the other one going that way. So of course, if you start near this with when they're already well separated, the next L, and if your magnetic field will make them go away, then you expect that this is a stable structure. And this is what we prove. So I recall that the dynamics here, they're driven by the magnetic field. So it's not pretty obvious that you require some assumption of the magnetic field. So you still need to assume that delta is small, because this is where you can perform the stability analysis for one domain wall. And you will assume this kind of condition, and it's actually very natural, this condition, because this is the Y star is the distance to Y star. So yeah, the idea here is that there's something that we know, and Y star. So this is the L, but at later time you assume you expect that you get Y star, and you will also get distance Y star for the second one. So there will be a distance to Y star, and this thing is actually control the interaction between the two domain walls. And what you want is that this interaction is integrable in time, and you can expect that this is. So it will just mean that, well, if you think that H is constant, then it's exponential in time, and okay, so it will be integrable. So the constant field will not do that. Okay, so how does it go? So you assume that at initial time, you give yourself a magnetization which is near the sum of two domain walls. And then you can prove that you preserve this structure for all time. And the point is that these error terms tends to 0. So the expression is a bit complicated, but I want to draw your attention to 2 things. The constant here are the constant of the initial data, the delta here, and this is the initial interaction of the 2 domain walls. And then you have decaying function, an exponential one, and then this kappa, which tends to 0 also. And you have a similar bound for the gauge, for the 2 gauges, except that you have here you have the L infinity norm of kappa, right? And here you have the L1 norm. So you have an explicit expression of kappa, which we can forget. I just put it here for memory. But the point is that the assumption on H will tell you that kappa is in L1 and tends to 0 at infinity. And as I mentioned, if it's bounded below, the convergence is exponential. And one sufficient condition is that H is essentially 1 over T. Take the exponential. Yeah, so I already said this. So you start with well-separated domain walls, and that's H pushes away, and you show that the configuration is stable. Yeah. So the idea is to localize in space, and yeah, the dynamic H. And this takes some inspiration again from the dispersive techniques. Well, the techniques developed for dispersive PDEs, notably the KdV and and generalized KdV equation for the stability of the sum of multisolid. Okay, so I can do a modulation around about 2 domain values, and here I have an extra trouble is that is not S1 valued, so I have to be careful, and I have extra terms which are related to the fact that my profile here does not lie in S2. This is the interaction actually. Y plus is essentially Y star, and Y minus is essentially minus Y stars. Okay, maybe, yeah. The extra ingredient is that you have to define a cutoff function. Place the cutoff function in the middle. So I cut off, side cutoffs the first domain will away, and then I have 1 minus. I define local quantities, and I do the expansion, and everything is basically as before, except I have error terms coming from the interaction of the 2 domain walls. These errors are the interaction of the 2 domain walls. These error. And I have errors coming from the cutoffs. But when I have errors coming from the cutoff, it means that when I do the computation, for example, for the dissipation, the derivative falls on the side. And I gave myself one extra parameter R, so that when I have one derivative, which falls on the side, and I get to 1 over R. And this, in the end, it will be this factor. So how do I complete the proof? The idea is to go back to adapt the proof for one wall. So first I choose the R to be absorbed, to be so small that I will have some coercivity, so it will be absorbed in the coercivity. And then I will relate, I have my capital A as before, and I relate my capital A's so that these error terms that I did in the modulation are small, and this is to absorb all the cubic terms in F star. So with the large R, I get rid of this, and with the relation between A and delta, I get rid of these 2 terms. And so what I get is this. Here I run type argument. It's a bit delicate because here it's okay. if I do the Grunwald type argument naively, then what I see that I have to integrate epsilon once for the Grunwald type argument, and then if I go back to the dynamic equation, I have to integrate a second time on G. So if I can integrate the interaction twice, I'm in business. And if you do it carefully, you see that you can it's sufficient to be able to integrate it once. But I give you more. Well, you do it, so it's a bit tricky, but in the end, you can perform your bootstrap and you're fine on the whole interval. But you also have to bootstrap the information that your domains are far away. So you have to integrate the dynamics equation, and you can do it. So you do it. It's the second integration in time. And you can bootstrap it again. And then you conclude by the same continuity argument. Okay. So yeah, I have a few perspectives on doing maybe what happens when you have two domain walls that go the other way around. So the collision problem. And we did some numerics, and many things can happen. You want to do what is not a perturbative result, but to start with any magnetization. What is do you have convergence? And also, you would like to do maybe 2D, like thin films and not nanowire thin films models, but this seems to be out of reach. Thank you very much.
Questions, comments? Quick one.
So the number gamma that has to be confined in between -1 and 1. So when it's bigger than those, then you don't have normal wall.
You lose a lot of things when you have gamma.
But you have those kind of special solutions still.
Yeah, it's not even.
So what is this gamma here?
Yeah,
Not make sense, right? So
It does not make sense. Right?
so then how does your stability, I would say if you send gamma to ±1, what happens?
Yeah, the constant goes up. The coercivity constant, for example, here, it depends on 1 minus gamma squared.
So at the linear level, you really lose stability.
Yeah, you will lose. Actually, for a constant field, you can. So it's not on the gamma, but they didn't use DMI. But I'm pretty sure that you can prove that with a magnetic field that is higher than 1 minus gamma squared, it's it's unstable. It's linearly unstable. If you send gamma to 0, then with a small magnetic field,